Hey, good evening, everyone. Let's just jump in. I'm going to try and get through the first part of this pretty quick because the good stuff is in the second half of the presentation. But please feel free to, stop me if you have questions. Hopefully, we'll have some time for office hours at the end, and we'll kind of go from there. Okay, so class 6, we're about a third of the way through. Hopefully, you've been seeing how the topics build on each other. Starting with fundamentals, we've got threat detection, now vulnerability assessment. And then next week, we're going to dive into malware classification. And let me know if you have any questions about how this all fits into the bigger picture. So we had the assignment last time. There's no assignment tonight. And we've got an assignment after lesson 7. So tonight we're going to talk about vulnerability scanning and penetration testing, prioritizing, predicting vulnerabilities, automated vulnerability discovery, case study. I'm on the fence about that. I have some things I think we'll probably end up talking about that are more interesting than a case study, and we'll kind of go forward from there. All right. So what is vulnerability assessment? It's proactive security. And we want to do this intelligently because this is one of the biggest sources, I think, in my experience, of false positives and churn and just a lot of noise. So, vulnerability assessment for code, vulnerability assessment for systems, software, it's all super noisy. And AI hopefully is going to take a chunk out of that because if you're a frontline analyst, tier 1, tier 2, you get tired of dealing with this stuff. I think with all the regulation we have and all the time and money we spend on assessing vulnerabilities and reviewing code and implementing compliance frameworks and all this stuff, I just got to say I've been doing this for a long time, and we're still trying to solve the same problem today that we solved 25 years ago, right? We still get attacked, and it's not the 0-day vulnerability, right? It's just bad hygiene. So it's the simple stuff, right? If you can figure out the simple stuff and take care of that, which is often hard because of scale, you're going to find yourself in a lot better position, and then you can focus more on kind of the esoteric things. So think about it through that lens, right? The reason that we don't manage it is because it's immense, and we have techniques at our disposal through machine learning and artificial intelligence to help influence that and really do something to make security better. So by the end of class, hopefully you can explain these 3 things: the role of AI in vulnerability assessment, difference between scanning and pen testing, and talk about how AI can prioritize and predict vulnerabilities. And, this is really the next step we're going to be taking when we talk about being an AI wrangler, right? We want to be the person that uses AI to do this, not the person on the front line that just has to deal with torrents of false positives and classifying those and doing reports. I know we've all done it. So we're trying to move beyond that, right? We want to get out of being in the swivel chair. Okay, real quick recap: threats and vulnerabilities. We've talked about this a couple of times, right? So, what's the difference between a threat and a vulnerability? A threat is, potential harm, potential compromise. A vulnerability is a way in. It's like an unlocked door. Threats are external forces. Vulnerabilities are weaknesses that they can exploit, right? The burglar always finds an unlocked door. And then, an example would be something like WannaCry, unpatched systems vulnerabilities. And theoretically, vulnerability assessment is how we systemically find these weaknesses. Being that we've been doing this since the early 2000s, and we're still having problems with these weaknesses, I would question as to the veracity of that statement. So what's the role of machine learning in vulnerability management, right? Um, it, it's a life cycle. Vulnerability management is a life cycle, right? It's continuous. There's a lot of data. There's a lot of moving parts. Um, the tools that we get from vendors sometimes don't meet our needs. Uh, and there's got to be a better way to do it because we're still drowning in false positives and non-applicable vulnerabilities, right? Uh, ML can help us enhance every step of the cycle. Um, if you've ever ground through a bunch of vulnerabilities, uh, something like Heartbleed, when I was at Microsoft, we got hit with Heartbleed, and you have to go through every potentially vulnerable endpoint, and you're doing it in spreadsheets. I mean, a couple of years ago. So, you know, I think the capabilities of ML can really help us figure this out. And so where it would take a week or two for analysts to do it, hopefully AI is going to do this for us in hours or days. So, and again, this life cycle is only strong as its weakest link. So, uh, discover is scanning, assess is comparison against a database, prioritize is the CVE score, probably, right? Report, that big giant spreadsheet that ends up in front of people with a bunch of pie charts that nobody can understand what they are. Remediate, questionable, right? You're opening Jira tickets to service teams and they're saying, this vulnerability doesn't apply to us, right? We don't even use this code. Verify, you run the scan again, you still have the same issues. So you're right back on the merry-go-round. Hopefully we can develop intelligent techniques using ML and AI that help us get off the merry-go-round and spend our time doing better things. So, three key capabilities I want to talk about here for automated vulnerability detection. And this is a little bit different. So traditionally, vulnerability management is signature based. And do you know my opinion on signature based? It's it's more about pattern matching. It's about matching the name of an executable, hash value, who knows, right? And it's garbage in, garbage out. It isn't context aware. There's a bunch of problems that we have to deal with every day as security practitioners that relate to this current approach. And what AI powered vulnerability management is it's a detective, right? It looks for patterns. It knows what normal looks like. And it can find things like, oh, gee, I've never seen this executable before, or it's a different size, or it's a different hash value, has some weird properties about it, like we're going to learn in malware analysis. It could be something about traffic to a network port. Maybe something's been compromised. Where is this anomalous traffic that's going to an endpoint in Estonia? Why is that on my network all of a sudden? I never used to have that, right? And pattern recognition. AI learns from the past to predict the future, right? If you think about clustering and some of these things we've been talking about, it's about patterns, right? What's like the other thing, and should I put it in this bucket? Is it normal? Is it not normal? It's very much like the way doctors work, right? They look at your medical history, they look at what's normal and what's abnormal. What do your symptoms correlate to, right? What's the potential diagnosis and what are some treatments? It's very important in things outside of cybersecurity, but same thing in cybersecurity, right? Is you're using history to diagnose what's in front of you, something you've never seen before. behavioral analysis, right? We can monitor user and system behavior for deviations. So, like we've talked about, employees accessing files they've never touched before, downloading data, strange hours, right? Differences in patterns. It's the shape we talk about, the rhythm of your environment. And what we're looking for is we're looking for things that don't fit. So, and what we want to do is we want to put AI in the center of all these different security functions. So, when we talk about the three major benefit categories related to vulnerability assessment, right? First is probably prioritization. All vulnerabilities are not created equal. Um, I think the prioritization of vulnerabilities by CVSS score, it sometimes is misguided because it assumes that all vulnerabilities are equal. Example might be is you have a vulnerability in a library on the service that would be potentially vulnerable if it was exposed to the internet. But if the host is not on the internet, do I care as much about it? Probably not, but I'm still going to cut that ticket and send it to them. And they're going to say, why do I care about this? AI considers context, right? Uh, could be things like like I just talked about. Is it internet facing? Does it have sensitive data? Is it a gateway? Is it a database server? Right? What classification asset is it? Do I care about this more than I care about something else? I should have some insight into that. So it would be like, if you run vulnerability scanning and you scan your lab and you scan your production environment, do the same vulnerability on a production system, does it rank as high as a vulnerability on a system in a lab? Probably not, right? But they quite likely get treated the same. Um, Automated remediation, right? AI doesn't just find problems, it can help fix them. We put a system together at Google that would automatically remediate vulnerable systems by putting them in quarantine, right? And taking them off the internet so they're not accessible until we could contact the users or the system owners and see if it was actually something that they needed for production or not, right? Patching with rollback capabilities, right? That's something that's hard to do. AI powered systems can handle some of this today. Firewall rule adjustments like rates and speeds and feeds and ports and things like that. AI enabled technology today allows automated control and management of some of these capabilities and parameters, right? This is a big one that's coming to the forefront, enhanced incident response. Uh, Faster detection means a smaller blast radius. I would say as advanced as you might think that some big tech companies are, I can tell you from personal experience that this is still in its infancy. Um, I think there's a lot we can do with AI powered runbooks and using agents to collect technology and feed it to analysts if we detect an anomaly. So we use ML to analyze our traffic. We decide what's an anomaly and what's not. If we find something that's high confidence or high risk, we route that to an analyst, but we also give them the information that they need to start investigating. Maybe we start a forensic capture. This is a really fascinating area where things are evolving rapidly, and I think you're going to see a lot of lift because nobody likes being tier one in a SOC because it's a thankless job, right? Tier two is not a lot better, but at least you have tier one to filter things out for you. So what we want to do is we want to repurpose those people so that they can look at high confidence alerts and take care of those instead of spending all our time on low confidence, low priority alerts. And the value of going through and filing this is a false positive report could be spent doing something else. So we need to get to the point where we have AI and it's capable of doing that reliably. So AI is going to transform vulnerability assessment from burden, right, into a competitive advantage after 20 some odd years of saying it's going to do that. So we'll see. All right, so what are some of the challenges? So there's three main challenges with ML and vulnerability assessment, right? False positive. Too many false alarms and teams ignore real threats. So this is kind of where we're at today, right? Is every time we have more detections or we turn more things on, or we say we need to catch 100% of the bad things, we inundate our analysts and our SOC. So how do we have a more intelligent approach to that? We'll talk about some strategies. But this is still why human oversight is critical. Somebody needs to say, hey, the way we're approaching this is incorrect. Here's a better way for us to take a look at it. And that's where our jobs are not going away, because we're going to be able to tell people how to do that. So human oversight, again, remains critical. Evolving threats. AI models can be outdated quickly. Somebody needs to keep updating, right? Continuous learning and retraining are essential to doing this. So that's where the human in the loop is essential to keep us up to date and keep things where they need to be. Integration complexity. I don't think that Claude is going to be able to go into an enterprise environment necessarily and figure out how to implement a better solution, right? So that's where you, as a subject matter expert and somebody who is an AI wrangler and knows about machine learning and artificial intelligence, is going to be crucial to help them move things forward, right? We have to deal with legacy systems that weren't designed for AI integration, but they have data. We can use data. They have an API. We can use an API. We just need people that can glue it together. And that's hugely expensive. So, as the human in the loop, we need to take charge of that and make sure that we can see that through. So AI is powerful, but it's not magic. And the challenges are real, and it needs a person to manage them, not an AI. All right, so vulnerability scanning, I think everybody's heard of this one. So this is, if you have a checklist and you use data and it's empirical, you can be pretty certain. But scanning's imperfect, as we all know. It's limited. There are definitely blind spots. We're reliant on CVE, right? That's everything we know about. But what if it's something we don't know about? It's the library approach as opposed to the we're going to find some anomaly approach. This is, I'm sure, is review, but basically what happens is the scanner connects to systems. It enumerates ports and services that are accessible, which is the first weakness, right? Shields up, you don't see anything. But what it can see, it checks against a database of known vulnerabilities, right? Unless you're lucky and you have an agent where you're behind the shields and you can see everything that's going on in the system. That's good. And then it sends you a dead letter office report with severity ratings that aren't context aware, that are strictly based on CVE and CVSS. And, that's kind of where we're at. So limitation, again, is it only finds what it's looking for, known vulnerabilities. It doesn't know if it's exploitable or not. This is a huge problem, especially with code. We're going to talk about this again in a little bit. And you get lots of false positives. So things haven't moved a lot. I think they're getting better, but Nessus, Qualys are a couple of popular scanning tools. And I'm pretty sure that probably everybody's touched on vuln scanning or been around it during their career in InfoSec. Another approach is pen testing. This is a generally human driven, which means that you have a hard time scaling. This is a skilled burglar where they have an adversarial mindset. They're looking for vulnerabilities. Burglars don't break into houses unless they are after something specific, right? And this is someone who uses the same tactics, tools, and processes that our adversaries use. Uh, this isn't testing, right? This is uh, an operation where you're looking to achieve an objective. It doesn't cover everything. It covers a very narrow scope necessarily. Uh, and typically you're looking to access data, escalate privileges. Um, so those are two of the probably the most common ones. Uh, you can subvert a code base. There's lots of different things, nasty tricks that pen testers are executing against us, but it's all useful. The problem is that you can't get 100% coverage, right? There's not enough pen testers. There's too much attack surface. So in a limited scope, this is great, but it doesn't scale. Pen testers are expensive. Who's tried to get a pen tester lately? If you don't have a team on your staff, if you're not a big tech company, good luck. And your mileage may vary. Not all pen testers are the same. And again, this is a point in time. Your infrastructure changes, and they have a limited amount of time and a finite amount of scope. So it's quite possible that things will get missed. And this is another checklist kind of thing. It's like, did you have your annual pen test? Yes. What did you test? One API or one feature or one API? That's still a pen test, so you can check the box. All right, so here's a comparison between scanning and pen testing. The For vulnerability scanning, this is automated. Pen testing, they do scanning, but a lot of manual work to figure out if something is actually exploitable. The goal is different: identification versus exploitation. Broad scope, low depth, targeted deep dive for pen testing. Output is a spreadsheet of vulnerabilities. Pen testing is proof of exploit impact. Maybe we got your data, we left you a little present. Vulnerability scanning cost is low in a single instance, but the aggregate cost may not be insubstantial, especially when you consider the burden on teams dealing with false positives. Pen testing, the cost per engagement is probably higher, but you might get a better result. It might be worth it. Vuln scanning is an ongoing process. Pen testing is probably a compliance checkbox for people. Maybe we're going to do it every year or two. And vuln scanning, it's like, here's a list. And pen testing, you actually have to show that you got something. All right. So what's AI's role here? Is we don't replace the methods, we make them smarter, right? AI can help scanners be more like pen testers, right? It can analyze some of the findings, and it can use AI models to help surface the most impactful results. It can do correlation between system type and risk profile. Speed and scale, it can analyze thousands of systems simultaneously because AI scales a lot better than humans, and reports just aren't cutting it. Accuracy, right? We want a better signal to noise ratio. We want less false positive reports to fill out, and we want more true positives going to analysts, and we want to be able to show that we're doing the right thing. We want to be able to say what's real versus what's predicted, right? And it's a continuous improvement as opposed to just feeding the machine. And you can also get proactive insights and try and figure out what the attackers will target next. We should be using AI because our adversaries. So this is where the field's heading, right, as towards AI augmented vulnerability management and security teams. Okay, so AI for prioritizing, right? Is CVSS the be all end all? Without context, I don't think so. Without analysis of whether they're true positives or false positives, I don't think so, right? It's just a number. So when something comes along with a high score and it's like, oh my gosh, all hands on deck, the cost to everybody is high, that it's unplanned work, so it's an interruption. And you have people asking the question, hey, does my test system in the lab really need to be patched with the same priority as my production system? And this helps us figure that out. You know, a typical enterprise has tens of thousands of vulnerabilities, and security teams are overwhelmed by this. A lot of times this is required for compliance. And unless you take an intelligent approach to this, it can be overwhelming. So AI helps out in a number of different ways. It does contextual risk scoring. So it considers things like, is it internet facing? Does it process sensitive data? Could consider what's the business impact if it's compromised based on your system architecture. It can demonstrate what factors are important, like asset criticality. Is an email server more important than a test server? Is it exploitable, right? Are there working exploits, or is this just something that's theoretical? Are attackers actively targeting this, right? These are all things that typically don't get thought through 100% today with vulnerability management. And this would be super helpful, right? Because let's prioritize the 10 or 15% of things that are really critical, and then we can put the rest of these on a normal patch thing. So, from the standpoint of being able to predict vulnerabilities, this is super helpful, right? Because we're not just kind of shooting blind. It's like all vulnerabilities are not equally accessible or exploitable, and we should be able to know which ones are. So AI can predict which vulnerabilities attackers will likely target. And then the benefit is that this focuses limited resources on highest impact vulnerabilities first. Okay. All right. So now let's talk about the fun stuff. So again, created some notebooks. I've uploaded this already. And basically what I did is went through, and for all the things we talked about, I said, let's show an example of how we would do this using Python and Jupyter. This again is code that is generated by LLM Claude, my favorite. And, we've got some visualizations to go along with it too. So the first thing I want to talk about is vulnerability risk prioritization, he said. So what we want to do here is we want to create an AI system that helps security decide which vulnerabilities to fix first, right? We need to prioritize so we can use our resources most effectively. And what this demonstration does is it uses a random forest to go beyond simple CVSS scores. So what this does is it combines traditional metrics with contextual factors like asset criticality, internet exposure, exploit availability, and this helps you decide which vulnerabilities to fix first. So this goes all the way back to stuff we worked on back in the early 2000s at Microsoft, right? Where we said we need to consider is a vulnerability detectable? Is it reachable? And is it exploitable? And that's how we started scoring Windows vulnerabilities when we first implemented Patch Tuesday, right? So this was a kind of a big watershed for us at that point. And so what the risk prioritization does is it combines multiple risk factors. So it's not just CVSS. It weights them to reflect real priorities. You know, internet system facing systems are riskier, right? They're more reachable. And it creates a realistic ground truth to train the AI model. So why did we choose random forest? Because it handles mixed data types, numeric and categorical. It can provide us feature importance, right? What factors matter most? If somebody says, well, what's more important? CVSS score, or if it's internet facing, or, you know, how old is it versus the system uptime? How many people have ever had a conversation where they say, oh, this vulnerability has been around for 300 days, so we need to get it fixed immediately, right? So, you know, these are the kinds of things that you want to be able to have a discussion about. So it's robust for outliers, right? Which are common in security data. And, you know, it has good interpretable results, right? Which is important for you as a security team. So, you know, feature importance analyzes business value. It shows which factor drive priorities. And this is transparency for security teams, right? Explainability. Uh, you can validate this with domain knowledge. Do the results make sense? A business analyst probably doesn't know. A security engineer or TPM probably does, right? And are we collecting the right data? So we focus on important features. Could you imagine how big your data lake would be if you had every piece of every log for all your security telemetry in your security data lake, right? Let's only collect the stuff that's important. We can keep the rest for historical purposes, and we can go back and do deep analysis against it. For our frontline systems, for security purposes, right? We only want to keep the data that is important to us. So what the big thing here is that ML can improve the traditional CVSS scoring with the organizational context, right? Where is it at? In this model run that we did, we got 97% accuracy in identifying high priority vulnerabilities. And the key factors are asset criticality, internet exposure, and exploit availability. So let's take a look at this real quick. So so what we did is we generated 1,000 vulnerability records. Again, this is synthetic data, but you could adapt us to do this with actual vulnerability data. And we have these features in the data set, right? The vulnerability ID, and then, you know, the asset criticality and things like that. And this is what we use to build this graph, right? And then from the vulnerabilities that we generated, right, we said that we had 30% conveniently, right? Because it's synthetic data. You know, we, out of 1,000 samples, we did an 80-20 split for training. And then we trained the random forest for prioritization. And here's our accuracy that we talked about. And then here's our classification report, right? Precision recall, F1 score. See, that F1 score is really good. So if we were looking at rock graph and area under the curve, remember we said it needs like to be 0.7 or better for it to be good. So our F1 score here is great. And then support is, we have lots of support vectors, right? So if we're doing like one class SVM, we would easily be able to see what's good and what's not. And then we were able to look at the feature importance, and then we graphed it. So this is pretty cool, right? So if anybody was to say to you, of the data set that we have, what are our most important features? You could show this kind of graph if you had done this analysis on your data. Okay. All right. So let's talk about AI for predicting vulnerabilities. And this is, how do you look into the crystal ball and forecast in the future what is a vulnerability? It's not fortune telling, it's pattern recognition at scale. Um, when I was at Amazon for Project Kuiper, we had a huge code base and we wanted to try and determine where should we spend our time doing code analysis to make sure that we have the least amount of vulnerabilities. And what we were able to do is use predictive means to figure out where to focus our efforts based on factors related to the code that let us, instead of saying, oh, we have to look at everything, we were able to focus in on a smaller percentage of the code base, right? 15% of it. That was the most complex and therefore the most potential vulnerabilities. Um, so, the AI learns patterns in code that lead to vulnerabilities. We'll talk about these factors in a minute. Um, you know, uh, what's a buffer overrun look like if someone is coding it, right? That kind of stuff is known. SQL injection, creds in code, there's all different kinds of things that sometimes your SAST scanner will find, but it does it without any context. So, and a lot of times it treats everything equally. I'm just going to scan through all the code. What code is the most dangerous? Where should I do a manual code review? And we can help answer some of those questions. Um, you know, Historical data, similar software almost often has similar vulnerabilities, right? So, and you can look at history. Uh, when we did the first code, external researchers did review of code at Microsoft. This was uh, what they did is they looked at commits, right? How many commits? If there's lots of commits, uh, and they keep having the same problem, then the problem goes away, right? You want to kind of look at that history. So based on those types of patterns, right? If you say this was a vulnerability and this was the history of the development of this piece of software, if I see similar patterns in the future, that might be a place where I want to look a little bit harder. So AI can predict where and when new vulnerabilities might emerge based on looking at your code base at scale. And this is better than things like pre-submit rules because again, it's a rule, it's static. And what we want to do is we want to analyze live data and come to a conclusion. Software dependencies, this is huge, right? Third-party libraries are super risky. Unless you have a good third-party code security plan, right? This can be disastrous. Oh, we're just going to download a Docker container and run it in our environment and, let's go. I have seen this issue with commercial code where you take a dependency on a library and then once you go and start looking at the library, you see that there's helper code in there that all you need to do is uncomment a line of code and it opens up a SSH port or a HTTP listener or callback to the person who owns the code's library. So happens a lot with commercial stuff. So beware there. And we can use AI to track dependency chains and also how vulnerabilities could potentially propagate. So this is shift left, right? You've heard this before. We need to find and fix vulnerabilities during development, not in production. So if we're looking at our code before we commit it and deploy it, as opposed to looking at it after it's in operation, it's a much cheaper to fix something before it gets pushed to prod than it is to deal with a patch or emergency patch. So, can we predict 0 days? Maybe, right? Behavioral aspects. if I've never seen a particular behavior before, right? Scarcity, that might be something. I think I've told you this story before about finding targeted exploit code in Windows error reports, right? That it's the same kind of thing. Uh, maybe I can't predict it, but maybe I could find it sooner using machine learning because I'm looking for outliers. Um, and this is becoming more and more prevalent in secure coding tools and DevSecOps pipelines. So let's talk a little bit about the example. So this is some code I put together to do vulnerability prediction. What does this do? It predicts how many vulnerability software might have based on code characteristics, like implementing the concepts we've talked about for AI and predicting vulnerabilities. So it predicts a count based on code characteristics. It uses software metrics around complexity, coverage, developer experience. And this really does enable shift left. And I've used this technique successfully in a couple of very large companies. So this really does work. The characteristics, I think the thing that people overlook a lot that has been super useful to me for many decades is cyclomatic complexity, which is the depth of code. How many depths of nesting does it have? So this helps you focus effort on your security testing on complex code. Developer experience again. Uh, this is a key thing. Just dumb things like looking through code comments for to do, or this doesn't work, or curse words. Who knows, right? There's always interesting things that you can find in comments. So if you'd used NLP techniques to scan your code base and tried to figure out what was going on with comments, maybe you would find a pattern. Who knows? Um, this is, again, lines of code that stands to reason more codes, more bugs. Um, I just talked about cyclomatic complexity, code review coverage. Reviews catch vulnerabilities, but you can't review everything. So how do you figure out what to review? Lines of code, cyclomatic complexity, right? That's always a good way maybe to prioritize your efforts. And then more experienced devs make fewer mistakes. What if your developer is an LLM? um, I don't know, could be good, could be bad. I was reading an article today that said 50% of LLM generated code has security vulnerabilities. So I think Andrew brought this up in a previous class, right? After you have code, don't just deploy it. Make sure that you go through and do a security review of it. And you'll thank me later. Uh, so what's the difference between regression versus classification, right? We want to predict a count, how many. We don't want to have just a binary decision of vulnerable versus not vulnerable. And we want to make this actionable for development teams, not just kind of vague hand wavy stuff. So, and this is super important when we talk about shift left. Jose? Okay, hands down. Sorry, missed it there. I was off on a tangent, man. All right. So again, this is in the notebook. Vulnerability prediction. Uh, we have synthetically generated 500 software packages that tells us the lines of code, the complexity, and again, there's more work required than just having this stuff show up. But for the purposes of demonstration, I'm using synthetic data. Can show you developer experience, testing coverage, code review coverage, dependencies, right? So you factor all these things together and it comes up with a prediction with respect to the number of vulnerabilities, which is pretty cool. Um, So
Hey,
how do
Stephen,
you,
quick question. Sorry,
yeah,
my mic wasn't working before. The developer experience, is that just years of experience? Or what is that direct value for developer experience?
I, my experience has been the years of experience that they've been a developer. So, um, but you could also slice it into the years of experience with a particular language. There's a couple of different ways you could treat it. Sometimes it's years of experience at a company combined with years of experience in a language. So, for instance, when I was at Google, they looked at how long you had been at Google versus, and also how long you had been working in a particular language kind of thing, because we did things sort of different. So, it varies.
Okay, so it
But
could be like some type of score as well. Like,
you
kind of.
could. I never thought about it that way. I mean, you could. I mean, you could do some feature engineering with that. You know, if you said, I want to know how many years you've been a developer, how many years you've been at our company, and how many years you have experience in a language, and you could use those to train your model too. That's an interesting thought. I didn't think about that.
Hmm,
So,
okay.
so I would say, but again, the you'd have to weigh that with the curse of dimensionality, right? If I had too many dimensions in it, am I worried about overfitting the model? So I would just pick one and see what I got. I always just thought, how many years have you been a developer? But that's an interesting question. All right. Um, and this is kind of what we came up with, right? Is the feature importance based on the model based on this data set, and this is kind of what we got, right? So, of course, it looks good when you're using synthetic data, but this is interesting. I've used these techniques in other um, lives before, different companies, and I definitely think this is a worthy model, right? Because you know we do find less experienced developers make more errors. Um, if we're saying it's 50-50, if you're coding with AI, if you're going to have vulnerable code or not, that would be something I would want to know. Is this a human developer? Is this AI? And then those various experiential factors that Jose brought up, I think are interesting to consider. Again, I would say pick one and see what you get, but think about those other ones, and you come up with a model based on that, right? Of course, it's always you're going to get more vulnerabilities if you do more security testing because the humans looking at it. I think that stands to reason. But again, how do you um, determine where you want to deploy the scarce resources related to people that can do code review and security testing? That might be some of these other factors. And again, this is how you do it with metrics as opposed to just making some broad statement like, you know, every red application needs to have a human security review, like we did at Amazon. Okay, so let's talk about automated vulnerability discovery. Uh, so this is how we're moving beyond finding known vulnerabilities to discover new ones. There's a number of different techniques we can use. There's fuzzing, smart fuzzing. This is super important. I don't think it gets done enough because it's hard. But let's talk about doing it more intelligently, right? Traditionally, I just throw random data at programs, right? Unless you got a good analyst and they're good with the tool and they can be more focused, you're just kind of spitting garbage at an API. And then if you're using an AI powered fuzzer, right? it can learn from successful crashes. So what made it crash? What's potentially vulnerable? Um, an example might be like Google has OSS fuzz, and that finds thousands of vulnerabilities, right, by doing intelligent fuzzing at open source. Um, Symbolic execution, which is where AI explores every possible path through the code. There are commercial tools that for years and years have said that they can do symbolic execution. Usually you get a giant spreadsheet that doesn't really tell you much. And what this does, though, is you're able to use AI to, pretty much give you infinite time to test every branch and condition because it can do it so fast, right? If you think about uh, what is it like, maybe like a tree-based algorithm, right? That it can do the nested if statement a lot faster than you can, right? I mean, that's LLM is a giant if statement. If an LLM can give you Python code, I'm sure it can do symbolic execution of your existing code. And this would probably find edge cases that humans would miss just because we're humans, right? We get tired, we get bored, and things fall through the cracks. Uh, I think there's a lot of promise here for automated code review. There's a lot of work being done in this space. We were working on it at Amazon, right? Where we teach AI secure coding patterns, and it comes back and it will flag deviations and issues in source code, and it is faster than human code review, available 24/7, right? Should be part of your IDE or whatever Jupyter notebook, right? Where it finds these things for you as you code and flags them. But if you had it going through a repo as well, that would certainly help. There is stuff like this deployed at scale. GitHub has a scanner where it looks through people's code as they submit it, and if it's these credentials and things like that, it will flag it, and it helps you from getting owned. So this is the key benefit here, is it finds vulnerabilities that a traditional scanner might miss or a human code reviewer might miss. And things like Microsoft Sage, MetaInfer, GitHub CodeQL are all examples of this. I also put an example together in a notebook. And this is kind of in two parts, right? The first part is, um, we're looking for anomalies. And then the next piece is kind of the smart fuzzing simulation. So let's talk about finding anomalies first. So if we switch over to the notebook, this is interesting, right? Because if we're looking for like anomalous communication activity, right, we would want to flag that. So we're not looking for an attack, we're looking for something weird. And this is the kind of use of ML and AI that is really kind of cool, right? Is uh, you know who's talking, what size is the packet, right? We've seen some of this in our malware analysis, right? Um, we will have another example of this later on where we look at a DDoS, and this is, maybe I find a compromised system. Um, so, of course, we have great results because it's a synthetic data set. But this is, basically we trained a model on these actual anomalies, and then we were able to turn around and through our test set detect them just as well. And why do we care about this? Uh, is we're using isolation forests to find anomalous, unusual network patterns. And, it picks up things that are different than the shape of our normal network activity, right? We've got the blue blob, right? We could draw a line around that easy and say anything that's outside of this is probably anomalous. you can see up at on the left, actual anomalies versus detected. You can kind of see where that decision boundary is because there's a few more things that are detected as anomaly than were actual anomalies. So that's kind of cool to see there. Uh, and this is something where it would detect unknown attacks and insider threats, right? So it's not signature based, but it's not normal, and it helps us bring it to our attention so that we can take action. Um, and we talked about normal traffic following a typical behavior pattern, right? Um, Anomalous traffic is something that doesn't fall into that pattern. Could be an attack, could be data exfiltration, could be support scans, and the uh, synthetic data was designed with realistic distribution. So it used the same sort of patterns that you would see in an actual attack. Why did we use isolation forest? It's unsupervised. It doesn't need labeled attack data, right? So it sees what's normal and then it sees what's not normal. Another way you could do this is with one class SVM, right? You could say, I want this, anything that is not in this blue blob is an anomaly and I want you to flag it. It's good for high dimensional data, right? That's maybe an advantage over one class SVM. So something like network traffic has lots of features. So it's able to work its way through those more effectively. It, isolates the outliers, right? Shows us what's rare and different. And it's fast and scalable, which is important because we use it for real-time monitoring. We standardized the data, right? We normalized it. Why did we do that? The different scales. We talked about this. We don't want, for instance, connection count to be overshadowed by packet size. This prevents bias towards large scale features, right? This is why we do feature scaling. And this improves anomaly detection accuracy, right? Because when we scale it, we're looking at how many deviations are you away from the mean, and the further that distance is, the more likely it is that it's an anomaly. All right. All right. So this is the simulation of smart fuzzing, and this is totally a simulation. This wasn't even synthetic data. And what this does is it simulates what it might look like if you did AI powered vulnerability discovery. And this simulates a AI guided testing with realistic success rates. And what the insight here is that different vulnerability types have different discovery rates. And what this means is the value is it's more efficient than just randomly testing things. So the simulation is that from the standpoint of being realistic, right, buffer overruns are easier to find, right? There's more of them. Integer overflows are harder to detect, lower rate. And this is based on so so this is super useful. It's a good add-on. And if you don't do fuzzing now, I would suggest you look into it because it is useful. You can do it at scale. You can fuzz a lot of your code, and you can find things with fuzzing that you might not find otherwise. So let's take a look at what this looks like in the notebook. So we talk a little bit about, the tests we perform, how long it took to find it, right? You can see it takes longer to find a buffer overrun than it takes to find some of these other things based on the algorithm. And then, based on the synthetic tests performed, it found this many vulnerabilities. So that was about, 8%, right? Which is about normal, right? Fuzzing can find, single digits. probably usually not more than 10-15%, but it's still useful because it's finding things that you might not find another way. Okay. So now let's talk about risk scoring. So this is we're kind of building up to something here. And it's this. How do I treat something intelligently with respect to how much risk it has? And this is the contextual piece of it that is going to be really important if you want to apply these techniques. Niraj, you got a question?
The a question with the previous slide.
Uh-huh.
Can you go to the previous slide? Yeah. So what is the difference? I mean, there's difference. I'm not able to exactly understand the difference between these two graphs: vulnerabilities found by type and the success rate by vulnerability type. What do you mean by success rate by vulnerability type?
It's how many it's the how often you find the vulnerability. So there's the number on the left, and then there's the success rate. Like if I test for a buffer overrun, how often do I find it? So
okay, so that's the success rate.
Overrun is almost 18%. And this is again is synthetic data, but what we're really looking at is I find it when I test for all these vulnerabilities, I find a buffer overrun. When I look for it, I find it about 18% of the time.
Okay.
And I found, 37 of them, let's say.
Oh, so that one. Okay, the number vulnerabilities found. Okay.
Does that make sense?
Okay. Yeah.
Right. Did that answer your question?
Yeah. Right. Okay. Thank you.
All right. Cool. All right. Okay. So risk scoring. So this integrates all these techniques that we've been talking about. It shows you what the role of AI and vulnerability assessment can be done. So we're going to integrate these multiple techniques and we're going to come up with a unified score. We're going to take a hybrid approach where 60% of the score weight is from AI and 40% is from CVSS. And this is going to let us make better decisions as security teams, right? So what the benefit is here is that because it's automated, it can process a large data set. It uses pattern recognition to find those relationships. It understands the context and it forecasts future risks, right? Real challenges with doing this are false positives, right? You have to make sure that your anomaly detection has good accuracy. You need good training data. You need to make sure that you understand and can explain what the AI is doing, and that you're comfortable combining these multiple techniques. So this is pretty cool because what we're saying here is with a traditional CVSS score, the oops, sorry, I don't know where it does that, but probably because I'm moving in that direction. It is that if you look at it, the AI enhanced risk score, the top risk score is lower than it would be for the traditional CVSS. You can see that CVSS is biased towards the right. There's a lot of 8s and 10s, and there isn't really anything above like a 7.5 for the AI enhanced score. So by having that contextual awareness, you don't just automatically say that because something is a vulnerability and has a CVSS score that it's a 10 and I need to do an emergency patch, right? There's not that many emergency patches in the AI enhanced lane. And also, you know, what's the relative importance? You can see with the traditional score, it's almost a solid line. So it says that things that are have a low score are just as important as the things that have a high score, right? So I think it's a more intelligent view of how these things play together. Implemented this in the notebook, and you can see here kind of what went into this. It can tell you the top 10 highest risk vulnerabilities, right? Based on the risk probability, and it gives you a comprehensive score. So you can see a CVSS score combined with the AI risk probability gives you a comprehensive risk score that is not a 10. So it's a little bit easier to deal with. And then it can also tell you, you know, what the asset criticality is. So this number on the left, these are just asset numbers from the synthetic data. It would probably be a host name or a GUID or something like that in an actual environment. And you can see it also has determined what the asset criticality is. That's a whole nother tangent we could go down, whether you score it yourself or whether it gets scored autonomously. But you know, obviously something that is in a frontline service is much more critical than something that's in a test lab. So there's lots of strategies for determining asset criticality. And then you know, is it internet facing? So all these things are kind of combined together and give you this view. All right. So where does that leave us? We wrote some code. We got some cool things on our Jupyter notebook. But for Tutu's sake, what am I going to tell the stakeholders? Right? Well, Streamlit can help you. So James, you have a question?
Yeah, super quick. If we go back, there was the table that your model outputted ranking the top CVEs based on the AI risk score.
Yep.
I'm having a little brain fart right now, but I'm looking at the AI risk probability column, and I'm assuming it's going from top to bottom 1 to 10, as I can see on the comprehensive risk score. What else was going into this comprehensive risk score? Because I see the like number 8, AI risk probability of 100%. How is that factoring into the comprehensive risk score again? Just so I understand what's going into it, and I can take a look at the notebook later too. But
Yeah. Yeah, that would give you the details, but basically what it does is that's a composite of the other factors related to the asset and the code, and the AI risk probability factors into that, and it helps determine that comprehensive risk score. So if you wanted to go and take a look at the code in the notebook, it is probably a better explanation than I just gave you.
Okay. Sure.
All right.
Thanks.
We'll talk about that a little bit more. Okay. All right. All right, cool. All right. So much like Plotly, this is another open source Python library that generates a website that you can use to present data to stakeholders. And again, this is kind of a hack job. I didn't spend a ton of time doing this. I just wanted to demonstrate, you know, yeah, Tutu. I'm not hearing anything. Did you have a question?
Yes. I was wondering, we spoke briefly about the pen testing.
Yes.
It seems very complex for, very complex to really have a pen tester or for pen testers to successfully execute some of these functions within the AI. What are the tools that they're using right now, the AI tools that pen testers are using to kind of,
I think a lot of what you see with pen testing is they're using AI for automation and also to go through results. So pen testers are using AI to go through code, and they're using it to go through output from tools. There are some theoretic AI-driven pen testing platforms. I'll get some names and post them in the chat for you later. But it basically what that does is it lets you cover more ground as a pen tester, right? Because a lot of stuff is manual. There's frameworks that run on top of Kali and stuff like that, where it basically harnesses all the tools, and it can help point you in a direction as to which tool to use and what to do next based on what it finds by doing reconnaissance. Does that help? And I'll get you a list of some examples as well.
Yes, thank you.
Yeah, you're welcome. Okay. All right. So like we talked about Plotly before for doing some of the output that might be something that would be stakeholder facing. Another example of a tool you can use is Streamlit, and this is a Python library that that you can use to do visualizations for your code and dashboards. It does great interactive dashboards. I think it's pretty cool. And the dashboard I created, it has 5 sections. So we have one for vulnerability prioritization. And this is live running on my machine, so if it crashes, I apologize. It's a Mac, it'll never crash, right? So we have vulnerability prioritization. So this is a real-time ML model that it trained with Random Forest. You can adjust the risk threshold. It gives you feature importance, right? Showing what drives your priorities. You can do a visual comparison, a CVSS versus AI risk scores. This is a visual representation of kind of what we talked about in some of those previous slides. So you can see it here. I would spend more time playing with these visualizations to tweak them a little bit, but it's a demo, so I did the best I could with the time I had. Vulnerability prediction, right? This is software vulnerability prediction based on code metrics. Some of the things that we talked about. We have anomaly detection, right? This is a further take on what we had in our code previously. It looks at network patterns. This is isolation forest as well. Have interactive confusion matrix. I like this hover over aspect of it. Smart fuzzing. Here's this is a simulation, right? But if I wanted to, let's say I had smart fuzzing and I had actual data, it could give me this kind of output, right? Shows me the rounds of fuzzing and the vulnerabilities found and stuff like this. Again, this is static data. There's not actually a fuzzer running in the background. But then the big thing is, right, what's your executive eye candy, right? This is always, it's what the heck are you working on? Why are you doing all this ML stuff, right? This is the kind of stuff that we want to be able to put forth to executives. Kind of cool stuff like security posture assessment, AI impact on security operations, right? Here's a good one, right? We want to make sure that they know what we're doing. Some recommendations, roadmaps, and then just some raw data. But this is all the kind of the cool stuff that you can do with Streamlit. All right, so if you want to go through it panel by panel and talk about it, right? For vulnerability prioritization, we had started with synthetic data. This is a simulation of a real vuln scanner output like Nessus. And we trained a random forest classifier on this to predict the vulnerabilities and which ones should be a high priority. And we're doing a comparison of the AI risk score and CVSS only approaches. And this shows feature importance to explain what drives the AI decisions, right? So, and then, you see you can do some, you can just look at, highs of criticals, you can just look at criticals. This is pretty cool. Again, low effort. This was something that I brewed up in a short amount of time by using an LLM and saying, hey, make me a Streamlit dashboard from my Jupyter notebook. Key components of this, we've got the total metrics row. We always want to total things out at the top. Most people don't read much more than the top of whatever it is, the doc or what have you. And we can see that there's a difference, right, in the number of vulnerabilities identified between AI and just CVSS alone. We have a high priority AI, right? Which ones are ones that we should look at based on this. So we have 1,000 total vulnerabilities. AI says we should look at 294. CVSS says there's 315. So, I would probably look at the AI ones first. And then how accurate is the model? Of course, it's synthetic data, so it's going to be super accurate. And then with respect to the risk score distribution, right? This is the x-axis is the AI risk probability, right? 0 to 1, 1's 100%. Risk threshold is we're saying anything more than 0.7. This is how many vulnerabilities we think we should look at. And we've got the hover over here. We can change this number of software packages, the high risk threshold, right? We can move this if we want to. You can see you can probably move it to 6 or 5.5, and you still have pretty much the same number of vulnerabilities. Your anomaly detection sensitivity. So this gives you a lot of flexibility with respect to the different vectors. The scatter plot is the x-axis is traditional CVSS score, y-axis is the AI enhanced risk score, and the color is the asset criticality level. So I can click on that and just filter things out. And this reveals vulnerabilities where AI and CVSS disagree. So, you can see where the AI risk score is higher here than CVSS. So that's pretty cool. So the point being, right, things that are far away from the diagonal, right, are where the context matters the most. Feature importance, we talk about this a lot. What's the point of doing this is, that AI considers sensible security factors. I don't think anybody would disagree with any of these if you talk to them, right? CVSS score debatable, but I think the rest of them I feel pretty good about. And that's kind of what we have. So let's talk about vulnerability prediction. This simulates software data with realistic metrics. We trained a regression model to predict vulnerability count. This shows a relationship between development practices and security outcomes and demonstrates kind of a shift left concept. So the top row here is metrics again. Amazon, we always said bottom line up front, right? Just tell me what I need to know at the outset, and if I'm interested, I might read the rest of it. number of packages, the predicted vulnerabilities. Is there any high risk software? Of course not. And then how well does the model explain variance and vulnerability counts? And that's the R square squared. So it actually does pretty good. And then we've got the predictions versus actual plot here. The actual vulnerability count is on the x-axis. The y is the AI model predictions. And this red line is a perfect prediction line. And points close to the line are accurate predictions. And the ones you see that are further from the line probably is related to model limitations. But this gives you good context with respect to what's real versus what did we predict. And again, this is synthetic data, so this is a little too tidy, but it's just for the standpoint of being able to demonstrate that concept. We can talk about average vulnerabilities by language, code qualities, impact on security. This is code review coverage versus vulnerabilities, developer experience versus vulnerabilities. And you can click some buttons, make some points disappear and appear. But again, this is a direction you could go just based on your code quality metrics. Then let's talk about anomaly detection. This is behavioral analysis and finding unusual patterns that might indicate incidents. We simulated some network traffic with normal and anomalous patterns. We used isolation forest again, right? Seems pretty popular, hint, hint. And then we evaluate our performance like we do with everything, with precision, recall, and F1 score. Suspiciously high, but I'll take it. It's a demo, right? And then what's our precision, right? What percentage of flagged items are actually anomalies? And of course, we get it right because it's a simulation. Here's actual anomalies. Here's AI detected anomalies. And you can see they're pretty close. Maybe AI detects a few more. And I guess the takeaway from here is that attacks usually involve unusual data transfer patterns. So you could do, like, again, if you used a different algorithm, like one class SVM, you could say everything in here is normal and anything outside of it is anomalous, and you could probably do pretty well with that. But it is pretty clear from looking at this, right, what's normal and what's not, just based on density. We have our confusion matrix, which we always like to see. Our algorithms did a good job because it's simulation, and simulations are always good. We've got some traffic pattern analysis, but these are all examples of things that you can do, right? How many lines of code is this? So this simulation is 530 lines of code, 550 lines of code. I would have to look in Visual Studio to see how many lines the Streamlit application is. But again, did I need a programmer to do this? No. Did I need a data scientist to do this? No. Did I need a Streamlit developer, Python? No, I didn't. I did this all using an LLM. So this is the kind of stuff that you can do using these techniques that we're showing you in this class, right? Your knowledge is what's gonna power these things. We talked a little bit smart fuzzing, using fuzzing to generate or find anomalies. Again, this is a simulation, but this is the kind of stuff that you can do. You could, obviously a fuzzer wouldn't run this quick, but this would be how you could show the output of fuzzing, maybe not these exact metrics, but you know, you could show how many tests you're done, how many vulnerabilities it's found, what's the success rate, right? 12.9. I like that. Estimated time, don't think it matters, but you know, it's your dashboard. You can do whatever you want to, right? But what this does is it compares the success rate of AI powered fuzzing, traditionally random fuzzing. Traditionally random fuzzing, I used to teach this at Microsoft, a thing called Fuzz Guru, 1 to 2%, right? So if you're telling me that my smart fuzzer has a success rate almost 13%, I want 2 of them. So so that's pretty cool, right? That's hopefully what smart fuzzing is going to do for us. You know, we got some detailed results, some key insights, and you know, we could look at raw data. If we didn't want to look at raw data, we could just click it there and okay, Tutu, question?
Yeah, I was just wondering, what is this dashboard configuration that you are using? What system, or is it a software?
It's Streamlight. It's
Stream.
this is an open source library.
Okay.
This is like Plotly. So
Um,
you can just do pip install Streamlit into your Python kernel and you'll have it.
okay, we can put that. We can integrate that into our Anaconda. Is that what you're saying?
Yes, you can. So this actually is I have this running. I have this in Visual Studio Code. And how many lines is this dashboard? It's pretty big, but I used Claude to write the dashboard code, and it wrote me the Streamlit code, and this is like 967 lines of code. So I mean I couldn't write 967 lines of Python code to build this dashboard, but Claude did for me. So you know, play around with it and see what you get. I just basically said build me a Streamlit dashboard from the code in this notebook. So I took this notebook, I went to my AI, I told it to build me a Streamlit dashboard, and that's what I got. I mean, I had to fiddle with it a little bit to get it working. Some back and forth with AI, correcting some display errors and stuff, but that's pretty darn cool.
So all you have to do is your LLM and just prompt that for your LLM.
Yeah, I just prompted my LL and it wrote this for me. So no developer required, no data scientist required. Like I said, if you know how to go back and forth with the LLM to get it working, because there's always a few things that don't look right. But this was, I guess, surprisingly trouble-free. It was wasn't a lot of back and forth. There's just a couple of visualization things that I had to, and it was more format of the visualization than the visualization itself. It was just some, you know, weird columns and stuff like that. Jose, you had a question?
Yeah, can you hear me?
Yeah.
Did you have to ask for each one of these graphs to say, like, I want to see smart fuzzing learning curves, I want to see vulnerability found by type, I want to see fuzzing, like every single item? Or did you
Nope.
just say, like, suggest me or create a bunch of visualizations based off the data, and it suggested everything?
I just said create a Streamlit dashboard, dude. Seriously. And it took the organization of my notebook and incorporated that into the dashboard.
Wow. Awesome.
So yeah, so each one of these are like the 5 things that we had in the notebook. And I won't say that, I mean, before I played with Streamlit, I probably would have got really excited about these, but this is kind of ho hum when you can get this, you know. but it gets you from your notebook to the dashboard. It's kind of like the stuff we did with Plotly. So this is the jump, and if it's in a Jupyter notebook, the only people that's going to care about us is us nerds, right? But if you want the person that has a checkbook to pay us nerds to care, you need a dashboard.
So will this I know you said so the code for the data set is in GitHub. Is that for this what you
No,
showed?
this is
earlier?
synthetic data. So if you look at the notebook for this is all generated data. So all of this is synthetic. So, but you
I meant
could,
this notebook right here is available in GitHub.
yes, it
Okay.
is.
And
The
then
notebook,
the
the notebook's in,
code.
I'm
Sorry.
sorry, I keep talking over you. Go ahead.
No, sorry. I was just gonna ask, and the code for the Streamlit is separate than that, and so you have to have both.
Yes. So and that's in the Python for the Streamlit app is in GitHub as well. And I ran it from a terminal prompt and it launched a new web server. So Streamlit runs it as its own web server. Right. So I've got like Jupyter running on 8888, and this is running on 8501 on my local host, but it spawns a new web server. So basically what you're doing is you're running this in your Python kernel and it starts a web server.
Okay, great. So, okay, that was my main question is like, can we access both sides in GitHub? And it sounds like the answer is yes. So,
Yes, absolutely. The notebook is in notebooks. And if you look under main in code, the Python for the Streamlit dashboard is there.
awesome. Thank you.
Y'all, like I said, it's GPL. Y'all are welcome to it. And then I haven't played with this, but I think that Streamlit will make this deployable, so you could actually, make something that other people could access off your local host. But I haven't played with that, so don't hold me to that. I didn't feel like clicking deploy before class in case something bad happened. I'll do that this weekend.
Yeah, no, it does. It deploys the dashboard.
Okay. All right. All right. Where does that leave us? It leaves us out of time. I'm sorry again. So, but again, I'm just a dumb guy. Y'all can do this. I use all this is LLM generated code. I'm certainly not an expert in any of this, but I think where my expertise comes in is if you look at it and you say, okay, I look at the code, I look at the output, and does it pass the sniff test, right? Again, synthetic data, I think it would be a worthy project to try and go connect this up to some actual data. And it probably wouldn't be too tough to do, right? So instead of using synthetic data, you could point it to a data source and import a data frame and do that stuff that we've been talking about so far. But you're not that far from being able to do this probably with your own internal data. And again, this is great because this isn't going out to the web. This is all running on your local machine. Again, for a science project, you're probably okay. I don't know how well this would scale. You get to a certain point, the fact that it's just running in Python instead of Jupyter Notebook is probably better. So you'd probably get better performance. But this is where we're at, folks. This is the kind of stuff that you can bring to the table and, hopefully show the impact of using some of these new techniques. All right. All right, so that's all I got. There's a couple more slides here, but I'm over time. We'll post the slides. And we'll talk about this a little bit more with malware classification next class. But, being able to do this stuff, have the power of this, at your disposal, I think is pretty dope, right? I mean, 5 years ago, could you have done this as a TPM or a security analyst or something like that? Probably not easily, but you know, so we have a way to generate the code that does the analysis. Once we get the code that does the analysis, we can look at it in a Jupyter notebook. I can use the code that's generated in the Jupyter notebook, and I can ask my LLM to create a dashboard for me. And it's fantastic, right? This is, I mean, it's a game changer for all of us. And AI is not taking my job. It's not taking your job either, right? Because you're going to be the person that's going to make AI do work for your company. So that's what I hope you take away from this. All right. So we're over time again. Apologies. Get used to it. Sorry. I have so much to say. Hopefully it's useful. If you got questions, put them up on Discord. I'll check later, and I'll be lurking over Friday, and maybe I'll take a peek during the weekend because I'll be doing lesson prep. So if you got questions, ask them there. But hopefully, this was useful. I know we're drinking from a fire hose still, but you know, we'll get there. Again, this stuff is all accessible. It's doable with LLMs. And hopefully you're getting the sense that you have a lot of power at your fingertips. All right, so that's all I got. All right, folks, unless there's anything else, have a great weekend, and I will see you on Tuesday.